All right, so we had talked about mutual inductance. Let's do an example of mutual inductance. Let's say that we have an AC power supply and it's sending current through a coil. So this would be our primary coil. We'll call it coil 1. So the primary coil has 1750 turns. And let's say the diameter of the primary coil is 5 centimeters. So that's 0.05 meters. And let's say that the current being supplied varies sinusoidally, so it's going to be 2.15 amps with sine of 785 hertz t. Okay. Now remember, this is going to be sine omega t, so that's sine 2 pi f t. So the 785 hertz is the angular frequency. It's not the actual f. In this case, the actual f is 125 hertz. So 125 times 2 pi is going to give us the 785. And let's say this entire coil that we've got here has a height of 25 centimeters. Now, what we're going to do is we are going to wrap another coil around the primary coil and then go through resistor. So the secondary coil, N2, is going to have 375 turns. And let's make that 100. No, not 175. Let's make that 125 turns. So 125 turns. And let's say this is a 2.25 ohm resistor. And so the question is, what's the current in the resistor due to this sort of arrangement? And you say, well, the resistor is not directly connected up to the power supply, but the primary coil has current flowing through it, and the current is changing. The current flowing through the coil makes the magnetic field change. The changing magnetic field makes the flux change. The flux through that coil is going to be related to the flux of the secondary coil. And so all told, this means there's going to be changing flux in the secondary coil, which induces a magnetic field. And so, induces an EMF. And so we know that the EMF, okay, is minus M rate of change of the flux. Okay. So all we got to do then is figure out what the flux is and what the mutual inductance is. So we look at this, we say, well, we know that the mutual inductance, we'd already figured that out, is going to be N2, that's the number of turns in the secondary coil, times the flux in the secondary coil due to the first. Okay, so that means that's going to be the flux basically through produced by that first coil divided by I1, the current in it. Okay, so once again we're back to this magnetic flux. Okay, and so we want to find what is this M. Okay, and so the magnetic flux, well, that's going to be equal to, the magnetic flux is going to be equal to, basically that's the flux in that primary coil. And so the flux in the primary coil is going to be equal to B times A. Okay, so the coil is basically a solenoid. And so we remember that the magnetic field of a solenoid was mu naught N I times A. Now what is little n? Little n is the number of turns, so that'd be N1, divided by the length of the solenoid times I, and this is going to be I1 because that's the primary times A. So A, okay, A is going to be pi r squared. Okay, so all we have to do is plug that into M. So M N2 times N1 times mu naught times I1 times pi times r squared divided by I1 and L. And so the I1s cancel. Okay. And so what we have left is this is going to be equal to 1 over L, N1, N2, mu naught, pi, r squared. So that's going to be equal to 1 divided by 0.25 meters, okay, times 1750 times 125 times mu naught times pi times r squared, and r would be half of the diameter, so 0.025, so 0.025 meters squared. So the mutual inductance turns out to be 0.00216 henries, or 2.16 millihenries. So now we have the mutual inductance. Now we go back to EMF in the secondary coil is going to be minus mutual inductance, rate of change of the current in the primary. Okay, so what we need is the rate of change. So the rate of change of that current, and remember the current was 2.15 amps times sine 785 hertz T. Okay, and so the rate of change there, the derivative is now going to be equal to 1690 amps per second times the cosine of 785 hertz T. Okay, so now we plug all that together. So the EMF in the secondary coil is going to be minus 0.00216 henries times 1690 amps per second cosine 785 hertz times T. So the EMF turns out to be minus 3.65 volts times the cosine 785 hertz T. So all this is saying is that the voltage changes as a function of time, as a cosine. So that's the amplitude of it right there. And so if we want to find current, then we know that current is going to be V over R. So in this case, the voltage of the EMF over R. And so the current is going to be equal to the minus 3.65 volts cosine 785 hertz T divided by the resistance, which was 2.25 ohms. So 2.25 ohms. So the current turns out to be minus 1.62 amps cosine 785 hertz T. And so we have a current that changes with time, and this is the angular frequency. It's the same frequency as 125 hertz. So the angular frequency is still 2 pi f. And so that gives us a measure of the current. So it goes from plus to minus 1.62 amps, and it does so at a frequency of 125 hertz. So that's an example of how it used this concept of mutual inductance.